Okay, hello students. So today we are going to study about RC circuit. Okay, so let's talk about this circuit here. RC circuit stands for resistor capacitor circuit. Okay, it is an important topic because it has a resistor and capacitor, both the properties. Okay, where in the circuit, right? So both the resistors and capacitor, okay, work simultaneously as per their nature. So so far most of the time we talk about the capacitor in steady state. As you all know that there are two phases, okay, which we talk about generally when we study about the capacitor. Okay, so the first phase is like when the capacitor is in steady state. Steady state means like we can see here where the capacitor is fully charged. Okay, where it is fully charged. Once the capacitor, now this is a property of a capacitor, when the capacitor is fully charged, okay, when it's connected with the battery and it is fully charged, that means the capacitor, okay, has stored the charge, okay, up to its maximum capacity, so it cannot store more charge, okay, within it. So what happens here when the capacitor is fully charged, so it stops, okay, taking charges. So we say that the charge flow is stopped. And when we say the charge flow is stopped, okay, so the through the capacitor, okay, there is no charge flow. Okay, so that's what we say when the capacitor is in steady state. And there's a nature of a capacitor. The capacitor, there's a use of capacitor also, that capacitor stores the charge only, right? So now we are going to talk about the RC circuit. So basically and there's one more important thing, that when the capacitor is fully charged at steady state and there's a charge flow is stopped. Charge flow is stopped means that there's no current flow. And if there's no current flow, if there's no current flow, and if there's no current flow, then there is no use of resistor. Means normally whatever circuit we can imagine of, that each circuit will have a resistor. Okay, we cannot imagine a circuit without resistor. But normally when we talk about a capacitor, okay, which is in a steady state, so there we don't connect a resistor normally. Why? Because of this reason. Because we talk about a certain phase where the capacitor is fully charged, it is in a steady state. So there is no current flow, so there is no use of resistor. Okay, so that's why we don't connect a resistor with the capacitor when we talk about its steady state. But now we know the capacitor cannot be at steady state all the time. Okay, if we take a capacitor which is uncharged initially, okay, and it's connected with a battery, so capacitor will be charged. That the time taken by the capacitor to charge will be very low, okay, will be very less. But still, if you want to calculate the time, if you want to know the process through which it gets charged, then that will be the another phase of capacitor. So in this another phase of capacitor, where we are seeing that the capacitor is charging. Capacitor is charging. Okay, when the capacitor is charging, now there's a charge flow continuously. So this is basically a kind of a phase, okay, which exists between t equal to 0 when the switch is open and t tends to infinity when the capacitor is at steady state. So t equal to 0 when the switch is opened, t tends to infinity, like the capacitor has reached its steady state. So we are going to talk about this phase, ki what actually happened between these two times, t equal to 0, t tends to infinity. So now we know like that in this phase there will be a charge flow, there will be a current flow, so that's why there will be a resistor. Okay, we cannot ignore the resistor now. So now when I'll draw a circuit diagram, so I have to draw a resistor with the capacitor. Now you know when I'm connecting a resistor with the capacitor, that means a current has to flow, and current is flowing, right? So this is a V volt battery, this is capacitance C, this is resistance R. So when there's a current, so here now the capacitor is connected with the resistor here. So at t equal to 0, the capacitor is uncharged. Okay, capacitor is uncharged. That means what is the charge on capacitor is 0. Okay, so that is the condition I am taking here. Now let's make a switch here. Now when the switch is closed at t equal to 0, okay, so what will happen, the current will flow in this circuit because the capacitor wants to charge up, so there will be a current flow in the circuit, right? Now because of this current flow here, as we can see that the voltage drop at any instant, let's say now at any instant, the current in the circuit is I, and charge on capacitor is Q. So if I draw a diagram again with the capacitor, a resistor like this, so charge on capacitor is Q minus Q. So the voltage drop across the capacitor is Q by C. So if I say, like, assume it is 0 here, so this will be at V, this is 0, this is V. So voltage drop on the capacitor is Q by C. So what is the voltage at this point? So we can say it is V minus Q by C, and that will be equal to, if current is I, so that will be equal to, so V minus Q by C. From the circuit diagram, V minus Q by C is the voltage drop across R, because this V minus Q by C becomes 0 here. That means this V minus Q by C will drop on R, and according to the Ohm's law, this V minus Q by C should be equal to IR. Correct? So this is the equation which we get here, okay, at any instant. Now if we simplify it to CV minus Q by C is equal to IR, and like the I is the current, so it can be written as dQ by dt into R. So we just, let's separate the variables. CV minus Q is equal to, it is like kind of dt by RC. Now we'll integrate at t equal to 0. At t equal to 0, what is the charge on capacitor? 0, uncharged we took, and at t equal to t, the charge on capacitor is Q, okay, at an instant t. Now if we integrate here, so it is ln CV minus Q, 0 Q, and there will be like minus sign here, is equal to T by RC. This minus sign will go to the right hand side. Now if I put the limits here, so CV minus Q minus ln CV is equal to minus T by RC, and it can be written as CV minus Q by CV minus T by RC, and there's a base E, so we can say that CV minus Q by CV is equal to e to power minus T by RC. Now if we cross multiply, and if we get the Q value, which will be CV 1 minus e to power minus T by RC. So this is the charge now. You can see it is like exponential function here, and this exponential is basically an increasing exponential function, right? Means like from this expression, that if I put t equal to 0, so we can see that q will be 0, and when I put t tends to infinity, you just see here it comes to be q equal to cv. This point is important here, that at t tends to infinity we are saying that q equal to cv, and cv, if you see the circuit, cv is the maximum charge that capacitor can hold. That capacitor and resistor are connected with a V volt battery. Right, the total voltage drop on capacitor and R will be V, or we can say the maximum voltage drop on any of the element could be V only. So if I say that voltage drop, the maximum voltage, if I ask like if the maximum voltage drop on any of the element, what it should be? So it could be V only. So when that voltage drop on a capacitor is V, so the maximum, so the charge stored on the capacitor will be CV. So this is nothing but the maximum charge. So maximum charge on capacitor. Okay, so it can be written as Q max. So the formula comes out to be Q equal to Q max 1 minus e to the power minus t by RC. That's it. So this is important function now. See, when the capacitor is charging, so the charge comes out to be this one, and if you draw a graph, so q versus time, so q t equal to 0, it is 0 and it increases and exponentially increasing, and here it is CV. Clear? So just remember this graph here, and from this q we can find the current also. Now from the q we can find anything like which we want to calculate, like we can find the current here, we can find the energy stored here, we can find the voltage drop at any instant t, okay, voltage of capacitor at any instant t, right? Yes or no? We can find the force between the plates also with this q square by 2a epsilon naught. We can find the electric field inside that capacitor. So you can see here, like we can find everything, okay, if we know the charge on capacitor. Now from this charge here, like if we calculate the current, so I is equal to dq by dt, right? So it will be like so CV, right? CV and 0 minus e to the power minus t by RC and divide by RC, right? Minus RC. Clear? Now minus minus will be plus, so the ultimately the current comes out to be CC cancelled, V by R e to power minus t by RC. Now you can see here the current which is coming here, I equal to V by R. A V by R is again a maximum current in the circuit. I'm leaving this thing on you, that you think about it. What could be the maximum value of the current in the circuit, okay, and it will be V by R. Just think about it, okay, just 2-3 minutes you think about it. And now the graph of I versus time, so it is exponentially decreasing. So at t equal to 0 it is maximum I max, and it decreases, and when t tends to infinity, that I tends to 0, and when t tends to 0, when t was 0, so you can see here I was maximum. So the one thing is very much clear about the charge and the current. At t equal to 0, when there is no charge on capacitor, the current was maximum, right? And when t tends to infinity, when the capacitor is fully charged, the current becomes 0. So with these 2 points we can conclude one thing, and which is very important for our circuit problems. At t equal to 0, so this is the time that sometimes in the question they mention that t equal to 0, and sometimes they mention that just after closing the switch. And so this is the time when the switch is just closed. So just after closing switch. Okay, so there's a language like which you can see like in questions. So at t equal to 0, we are talking about the charging of capacitor. So at t equal to 0, the capacitor has 0 charge, right? The charge is 0. Current is maximum. So current is maximum. Okay, current is maximum and charge is 0. And when we say that at t tends to infinity, t tends to infinity means the steady state. Okay, steady state means there is no flow of charge, that we already know, or in the language sometimes they say that after long time, after long time. So after long time, what do we say? That the current becomes 0. So now, based on these two situations, what we can say, that at t equal to 0, where the current is maximum, the capacitor in the circuit, okay, at t equal to, what is the current maximum? V by R. That means capacitor is present, but still the maximum current is V by R. I mean, the circuit is behaving like a resistive circuit. I mean, capacitor is there, but when we are solving the current, it looks like the capacitor is not present. Getting my point here? So that's why the current is V by R. So that means the capacitor is there, which is behaving like a connecting wire. So you can replace that capacitor with the connecting wire. Connecting wire. And in the case of when t tends to infinity, the current becomes 0. That means the capacitor will behave like a broken wire. Means that circuit is broken, that's why there's no current flow in that particular branch. Broken wire. Okay, so these two concepts like we use normally in that circuit problems. Okay, there's a one more thing which is important, time constant. The charge expression which we see, that q equal to q max 1 minus e to the power 1 is t by rc. Now if we talk about a dimensional formula, okay, if we talk about something about the dimensional formula, so if I ask you what is the dimensions of RC, so if you know about the dimension formula and its application, so you can clearly say that exponential function is a dimensionless function. That is why the t by RC should be dimensionless. And when is it possible? When is it possible that t has a dimension t1? That RC should have t1 dimension formula. And here this RC is basically known as time constant. Because of its dimension formula, we are defining it as a time constant. Its value will be constant for a particular circuit. That's why like time constant we use. And what is the definition of time constant? So we can say, so sometimes we write time constant with tau. So if I say that, if I want to define the time constant, so if t is equal to tau is equal to RC, then q will be equal to q max 1 minus e to power minus 1 to 1 by e. So it comes out to be q max 1 minus 1, so 1 by is 0.37, so almost it comes at 0.63 q max. Or current, if we say, like it will be comes out to be 0.37 I max. So now what is the definition of time constant? So we can say the time constant is the time where the capacitor is 63% charged, or we can say the current in the circuit, is 37% of maximum current. Yeah, the remaining current basically. This is what? Remaining current. So current is continuously decreasing here. So the remaining current in the circuit is 37% of maximum, and the capacitor is 63% charged. So we can denote this thing in graph also. So this is the RC and this is like 0.63 CV. Okay, same thing we can draw here also. Okay, so that is about the charging of a capacitor. So I hope you understood this case. On the same side we have like another case where the capacitor is discharging. Okay, in the case of discharging, we'll be having a capacitor which is fully charged and connected with the resistor, with the switch. What will happen here? So in this case, like there's only one thing which will change, is that the equation which we wrote here, in this equation, that there is no V. If there is no battery, there is no V. So I'll put V equal to 0 and I'll write minus Q by C equal to IR. So it will be like so everything is gonna be same. Okay, I just gave you hint here. You start from here. Okay, dq by q is equal to minus dt by rc. Okay, you integrate t equal to 0, the charge is maximum, capital Q, yeah, q max, yeah, cv you write, and t equal to t, the charge is q. So I want you, so this will be homework question now. Okay, this is homework. So I explained everything in the case of charging. Now this thing I'm giving you as a homework, as a practice, self practice, that you try to do this question. Okay, and try to find the expression of charge and current. So I'll tell you the charge of the expression of charge and current is gonna be same, and it will be coming out to be q equal to q max e to power minus t by rc, and current is also I max equal to e to power minus t by rc. So these are the current and charge expressions. After getting these expressions, you draw the graph, exponential decreasing, define the time constant, everything. So this is like I'm leaving on you. Okay, so to try this thing here, now we'll be discussing some questions here on like based on these like charging and discharging cases. Okay, so let's say here, let's take a question here. Okay, so the question is, there's a capacitor which is connected with the resistor. The capacitor of capacitance 10 microfarad, and it is charged with 60 microcoulomb, connected with the resistor R, which is like 10 ohm. There is a question here. What is the first question? What find the charge? Find the charge on the capacitor. Charge on capacitor in the circuit at t equal to 1 millisecond. That is the question. So we see the diagram. The capacitor is connected with the resistor here, and the capacitor is initially charged. So it is a case of discharging. So charge we need to find. So this is the formula here. So first of all, you can see that maximum charge on the capacitor is 60 microcoulomb. So Q is equal to 60 microcoulomb. So I'm going to use the formula e to power minus t by RC. What is RC here? So simply calculate 10 microfarad it is into 10 ohm. So it is RC equal to 100 into 10 to minus 6, which is 10 to minus 4. Q is equal to 60 microcoulomb e to power minus 10 to power minus 3, 1 millisecond divided by 10 to power minus 4, which is coming out to be e to power minus 10. In the question, like the e to power 10 value is given, which is 20,000. So we'll just simply put the value here and we'll solve it. That's it. 60 microcoulomb into 1 by 20,000. Okay. So just solve this value here. So you can see here the charge is coming out to be 60 microcoulomb. So the answer is here 60 into 10 to minus 6 divided by 2 into 10 to power 4. So you can solve it 30 into 10 to power minus 10 coulomb. So that is the answer here. Okay, let's see another question on this one. So another question is, let's say there's a capacitor. This time we are taking it is uncharged and connected with the 6-volt battery and a resistor. Resistor is 24 ohm. The question is like find the current in the circuit just after. So find the current in circuit just after connections are made. Okay, so just after connections are made, that means t equal to 0, right? Just after closing the switch, just after connections are made, t equal to 0. So current in the circuit, so we know, like, so first of all we'll calculate the RC value, which is going to be okay. Anyway, the current in the at t equal to 0, right? So at t equal to 0, we know first of all that what happens to the capacitor. So capacitor behaves like a connecting wire, right? So capacitor behaves like a connecting wire. That means it will be replaced by a normal connecting wire here. So connecting wire. So current in the circuit. Okay, so what is the current in the circuit here? So what is the current maximum? V by R, right? So V by R, what is V here? 6 by 24, that means 1 by 4, and which is equal to 0.25 ampere, right? So that's the answer here. And there's a one more question in the same question, like find the current in the circuit after one time constant. One time constant means t equal to tau. After t equal to tau, which is RC, what is the current in the circuit? So current expression now will use I equal to I naught minus t by RC. Now t is equal to RC, so I is equal to I naught e to power minus 1. That's it. So I is equal to I naught, which is we calculate 0.25 divided by E, into 1 by E. 1 by E value is 0.37. So 0.25 into 0.37, and if so, it comes out to be 0.09 almost ampere. Clear? So that's how the questions can be solved. Okay, and energy stored we can calculate. Okay, let's if I ask like what is the energy stored, so U is equal to, you can write so we know the current here, so we can say Q square by 2C. Okay, so Q expression we know, to 1 by 2C, Q is C square V square 1 minus e to power minus t by R C the whole square. So here we are getting energy also half CV square 1 minus e to power minus t by R C the whole square. So the point is like we can calculate these questions now. Okay. Okay, now I'm giving one question as a homework. Okay, so you can write it down. Okay, so there's a capacitor and there's a resistor. Okay, capacitance is C, resistance is R. The question is like suppose T1 is time taken by capacitor to reduce energy stored half of its initial value, and T2 is time taken for charge to reduce to 1/4 of its initial value. Okay, to find the ratio T1. So T1 is the time taken by the circuit to reduce the energy stored to half its initial value, and T2 is the time for charge to reduce to 1/4 of its initial charge value. Okay, so charge and energy or both I have said. Okay, so just try to calculate and just give some time to it. Okay, T1 by T2. Okay, so just try to solve it. Okay, so that is the homework here, and answer, if you ask, so answer is gonna be T1 by T2 is 0.25. Okay, 1 by 4. Okay, so let's move to the next. It's like another type of questions here. Okay, so another type of questions like which comes here is to find the time constant. Okay, so that is about the basically RC circuit. So I hope like it is clear. Okay, some up to some extent. Okay, the RC circuit is basically like where we deal with the charging process, discharging process of a capacitor in the presence of a resistor. Okay, if it is connected with the battery uncharged, so it will be charged up. Okay, the charge will continuously increasing on the capacitor, but if it is connected with the resistor without the battery, so the charge will keep on decreasing. It is discharging basically, and in both the cases the current will be decreasing. Okay, time constant is a circuit type of questions. Okay, so let's calculate here. And okay, so to calculate the time constant basically, okay, we use one trick. Okay, like there's like kind of a method only, okay, which we use to find the time constant. So what is the trick to find the time constant? So in a RC circuit, okay, it's like there could be multiple resistors, so tau is equal to RC, but if there are more than one resistor, so we R equivalent C. So that's what time constant formula we will use. So what to do here? So what is the trick? So I'll write the trick here. So trick is to replace the battery. Okay, if there's a battery here, so replace the battery with its internal resistor. Okay, if it is present. If it is not present, so you can simply remove the battery. It's like replace it with the connecting wire. Okay, replace the battery with its internal resistor, and if not, then replace it with a connecting wire. And the capacitor, and the replace the capacitor with a kind of a terminals, or with the battery here, with the battery or with the terminals. Okay, and with the terminals about which we will calculate the R equivalent. Okay, about which we calculate R equivalent of the circuit. Okay, so that is the thing like which we are going to use to find the time constant. So let's do some questions here. So let's say there's a resistor here, there's one more resistor here. Let's say there's resistor here, there's a battery, and there's a resistor, and there's a capacitor. Okay, so I just made up a circuit here. So there's a capacitance, there's a V volt battery, and these all are the resistors. So find the time constant of this circuit. So what to do here? So follow this process here. Replace the battery with its internal resistor. The battery is ideal here. It has a V volt okay, voltage. Okay, so we can simply replace the battery. Okay, so I'll draw the equivalent replacement diagram here. So replace the battery with the connecting wire. That's it. And connect all the resistors as it is, and replace the capacitor with the terminals, or with the what to say, like battery here. Okay, so replace the capacitor with the terminals, so A and B. So now I'll need to calculate the R equivalent between A and B. So apply that series parallel combinations. So as you can see here, these two are in series, 2R, and there is a parallel, all are in parallel, R are in parallel, R by 2. So 2R and R by 2 are in parallel. So 2R and R by 2 are in parallel. So basically it is 2R by 5. And 2R by 5 is in series with this one. So 2R by 5 plus R, which is like 7R by 5. So this is our R equivalent. So what is the time constant is? R equivalent into C. So 7R C by 5. That's it. So this is the question, sorry, this is the answer of this question here. So there could be like so many examples which you can think of about this time constant. So let's do one more question on this one. So there's a battery here, but just like follow the process like which is written key what you need to do is, because otherwise like if you keep thinking, if you like do not follow that one, so that will be a like very complicated process to find the time constant. So R here, C here, R. So now you just see this diagram here. So again you draw the equivalent diagram. So battery is replaced with the connecting wire here. There's a resistor, and there's a terminals. There's a resistor here, resistor, R. Now these are the like A and B. So between R and A and B, what is the equivalent resistance? Okay, so you can see here what is this. So these two are in series here, R and R to R, and if I just imagine a battery here, okay, so the current will go, so what is it? So 2R is in series with this one, right? I mean the same current will be flowing here. Sorry, same current is not flowing. Okay, there's a R here also. Okay, I'll draw the diagram here. So this is the battery here, right? There's a resistor connected here, and there's another resistor connected like this, and there's a resistor connected here. Okay, this is 2R, this is R, this is okay. Now you can see this one and this 2R are in parallel, right? Yes, so 2R and R in parallel. So what is it? So there's a battery, and there's a resistor R, and there's a 2R and R is in parallel. So 2R and R in parallel, so it is like 2R by 3, right? Of this 2R by 3 is in series with this one. So 2R by 3 plus R. So it is like 5R by 3. 5R by 3, it is 5R by 3 is in parallel with this one then. So 5R by 3 in parallel with this R. So 5R by 3 is in parallel with this one R. Okay. So it will be 5R by 8. Okay, so 5R by 8 we have this R equivalent. So what is the time constant then? So 5RC by 8. So that's the answer basically. So the point is like where you need to focus is to work on that equivalent resistance. Okay, there's a part of current electricity, so I hope like you practice there. So that's about the time constant. Okay, let's do some more questions on the circuit problems where we will use the basic concept like at t tends to 0, t tends to infinity. Okay, so this is a question now where we need to find the charge. Okay, find charge on capacitor at steady state. And current in circuit at t equal to 0. Okay, so first of all, current in the circuit t equal to 0. So at t equal to 0, what do we know? That t equal to 0, the capacitor behaves like a connecting wire. Yes. So I'll draw a replacement diagram. So in place of capacitor, I'll draw a connecting wire. There's a R1, there's an R2 in parallel, and there's a battery with small r. So we need to find the current here. So for that we can calculate the R equivalent. So straightforward now. The R equivalent is R1 R2 by R1 plus R2 plus R. So what is the current in the circuit? So E by this R equivalent. So just put the value here, and that will be the current in the circuit at t equal to 0. But now when we need to find the charge on capacitor at steady state. So at steady state means t tends to infinity. To t tends to infinity, what happens to capacitor? It behaves like a broken wire. So this is R1, this is R2, this is battery, and this is E. So now there's no current in this branch here, so there's no current, that means there's no use of R1. Getting my point here? So this is A, this is B. So I can draw like another diagram with where I can see that this is A point and this is a B point. There's a R2 here. Okay, I simply removed the R1 because there's no use of R1 because there's no current in that particular branch. So this is A, this is B. So just need to find that potential difference A and B, and that will be your answer. Okay, that will be the potential difference across the capacitor. So what is the current in the circuit at this instant? So E by R2 plus R. Okay, and now what is the current, the potential difference across R2? Because R2 and the capacitor will be in parallel. So VA minus VB is equal to, we can write as IR2. So which is like ER2 divided by R2 plus R. So that is the potential difference. And now what is the charge on capacitor? CV. So CER2 by R2 plus R. So that is the answer. Okay. So there is no current flow in capacitor, so there is a broken wire. So I simply removed that capacitor and resistor, and this is A. At this point is A, so that means this is also A, this is B, this is B. The connecting wires are there. So A, the potential difference between A and B is nothing but potential difference between R2. Okay, because R2 and there is a capacitor basically. Both are in parallel. Okay, so potential difference will be same. That's why we got the same thing here. Okay, so that's about this thing here. So I hope like you understood here. So just practice some questions on it. Okay, there will be some questions in your textbook, in any the reference book. So but I said about all the important points in this RC circuit topic. So I hope you find it helpful. Okay, if you have any suggestion, any topic which you want to revise, like okay, from my side, just you can comment it. Okay, and just thank you for watching. Thank you.